Hello, I'm going to go over chapter 24, study guide. Sorry this video is coming late. Just got out of lab. I don't know why I'm having to explain myself. All right, good start. Here are outlined the sections that are important in 24. Why are they important? Well, because they're everything. And on the assessments, we pretty much have to go over everything. But what's good about going to SI, and someone that's been through the course, is identifying and filtering out the stuff that doesn't matter. First thing with halogenation, it's good to know the mechanism for. Sure, it's good in synthesis probably. We're going to want to know probably the mechanism for that, and it's also, we'll see, can be important in synthesis as well. Alkylation is it's better to know on why it's bad rather than good. So we'll talk about a couple issues with alkylation, briefly discuss halogenation, maybe a little bit of the mechanism, why it's important in synthesis. Acylation, same mechanism as alkylation, but better in synthesis. We'll make a distinction on that. We're not going to go through the mechanism. If you want to do that, look at your book. Nitration, sulfonation, probably the least important. With nitration, we'll get into this benzene diazonium ion. If you do it that way, it's important, but just nitrate, just sulfate, it's not the greatest mechanism. It's not going to be that important in synthesis unless it's at the very end. That doesn't say mechanism, it just says meh. Like, you should still know it. Last two are a little bit different, but something we never went over in OChem when I took the course. The two methods of benzoic acid production, which is great for synthesis, putting something in the benzyl position, always a good thing. And then creating this benzene diazonium ion, really, really good leaving group, so it can turn into anything. So that's also good for synthesis. Let's go through all of that now, okay? That's what to expect in this video. First off, let's start with halogenation. I need two things for halogenation. I need, benzene, and I need two things. I need my halogen source, so that can either be Br2 or Cl2, okay? Now that alone is I'll use bromine. That alone is not going to do anything, okay? We're going to disrupt aromaticity if we do that, if it even worked, which it wouldn't. We need some kind of Lewis acid, so I can use either iron tribromide or aluminum tribromide. Either one will work, okay? This Lewis acid, go over the mechanism, allows us to create first an electrophile, of which our nucleophile benzene can attack. I'll go through it that way. What I should have written down, but I didn't, really good acronym to know for the mechanisms for chapter 24. I'll start with halogenation here, and I'll go through sulfonation, and I'll write these in green. Nice little acronym here, okay? Isn't an acronym just a way to remember the mechanism steps? So for halogenation, coordination, addition, elimination. Friedel-Crafts alkylation and acylation is going to be coordination, hydrolysis or heterolysis, addition, elimination. Acylation is the same mechanism, coordination, heterolysis, addition, elimination. With nitration and sulfonation, they're the same. One little caveat. Nitration and sulfonation are going to be proton transfer, heterolysis, addition, elimination. The only exception to this is if you use fuming sulfuric acid, which you probably should because it speeds up the reaction. You don't need to go through the heterolysis step, okay? So if you're using fuming sulfuric acid, this just turns into proton transfer, addition, elimination. If you notice, they all end with addition and elimination. we're adding something, we're really substituting something onto benzene. And then that elimination step is what recreates that double bond and restores aromaticity. We're back to a more stable conjugated system, aromatic compound. I'm gonna say one more thing with that. Oh, so if there's one conceptual question, pretty much the only one that I can think of, chapter 24, is what's the rate determining step? It's always gonna be addition. When we disrupt aromaticity, we add our group on, substitute our group, okay? And elimination occurs at the end. So our rate determining step is always gonna be that addition step. We create that carbocation, which is bad, disrupt aromaticity, that's bad, high energy, rate determining step. Let's get back to halogenation. Nice to know because we don't know which mechanism is gonna show up. This is a good chart kind of thing to know. Okay, with this, just gonna go through it fast. I have Br2, okay? First step is coordination. A lone pair on bromine attacks iron, okay? And I create my electrophile. Br. Now, okay, I've created my electrophile. Next step is addition. Now, which bromine am I going to attack? Many students might think that, okay, electron-rich area is going to attack the positive charge. Not the case. I'm going to attack the terminal bromine, push electrons eventually onto that positive bromine here. That way we get rid of the positive charge, but we're going to add that terminal bromine. Once we do that, we're going to do elimination step, take hydrogen, restore aromaticity. We're done. Okay, so creating electrophile is probably the most important step in that one. Not going to go through with all that. Again, look at your textbook if you want the detailed mechanism. You should know it. What's really nice about bromination, especially, and you can make Grignard reactions out of chlorine, is being able to, okay, I've done halogenation out of bromine, great. What's even better, and what's more commonly done, is taking this one step further and making a Grignard reagent. So magnesium in its solid state and any type of ether, I'll use diethyl ether, it's my favorite, it looks like a spider, okay? Doing this, I can make a Grignard reagent, so MGBr, which can be abbreviated as just this nucleophilic species here, okay? So I get MGBr, and then we can just assume that that is R minus. This then, so synthesis, maybe this is at the end, but it's more likely going to be a first step. We turn it into a Grignard, and we keep doing stuff later on with it. That's the the biggest reason why halogenation is important. Not really the halogenation, but what comes after it and making it a Grignard. There's halogenation, that's what's important with that. What's important in alkylation is that there's two things that can happen that we don't want. The first thing is a carbocation shift. So a benzene, I want to add, let's say I have a synthesis and I want to get to, or it's not exactly a synthesis perhaps, but I want to add a long carbon chain onto benzene, okay? Now, if I try to do that with alkylation, with this here, and I'll need some type of Lewis acid, I'll be left eventually, once after that coordination step and that heterolysis to create that carbocation. Let me actually show that. So chlorine, same step as before. We create our electrophile. 1, 2, 3, 4, 5, okay? Heterolysis step here. I need to break a bond, and I also know I need to make a carbocation out of it. So which bond's going to break? Correct, this one, going to go on to chlorine, get rid of that positive charge, which is good. Now I'm left with a carbocation that looks like this. Will a shift occur? Yes, it will, okay? Most likely I could put a hydride shift here, and I could probably add it here. Yeah, I could do probably the most reasonable would be a 1-2 hydride shift, and I'd get a secondary carbocation. Another way of saying that, I wouldn't get this thing. I would probably get maybe something like that instead, okay? So that's an issue if you want to make certain alkyl groups on benzene and it's not working out. The other one is polyalkylation, which is probably more important in later chapters, but benzene is electron rich. Okay, it's a nucleophile, electron rich. Alkyl groups are electron donating substituents. So we're adding, once we add one alkyl group on there, now we're donating more electronegative charge to something that's already electron rich. That's what makes it reactive. So we were now even more likely to put more alkyl groups onto this by adding just one. So once I'm to this point, I'm probably going to get to that point as well. Okay, polyalkylation. So it's nice to know rearrangements. The rearrangement part is the most important. Okay, there's really no other reason, I don't think, to put an alkylation problem on there unless it's a rearrangement. So be comfortable with that. Probably expect a rearrangement to happen at some point on the assessment with alkylation. Okay. How do we avoid rearrangement? We use acylation. Acylation will avoid rearrangements, so we can make something that looks like this. We just need to use acylation instead, okay? So I'll do the same thing. I'll start with benzene, but I need to use some type of acid chloride or acid bromide, probably more likely acid chloride, to match this carbon chain. Acid chloride, Lewis acid, and boom. I will get this compound here. There's no rearrangements that can happen, okay? Create my nucleophile, heterolysis, addition, elimination, I'll get here. Now, how do we get rid of that, that ketone? With benzene, you can use Clemenson, you can use Raney nickel, or you can use, what is it? H2NH2, Wolff-Kishner. So you can use any of them on benzene, they'll all work. Choose one you like and stick with it. Because with acylation, especially in synthesis, you usually make the acylation to avoid the carbocation shift, but you might not want that ketone on there. So get rid of that ketone, use Clemenson, use Wolff-Kishner, use Raney nickel. And then I believe it's HCl or some type of acidic environment down here. Don't quote me on that, but just stick with one and be comfortable with it on using that in case we need to get rid of that ketone group. So I use some type of reduction, again, Raney nickel, Clemenson, Wolff-Kishner, and so I can add any alkyl group really I want. It's just if I want to, I can always avoid a shift if I just use acylation and I use some kind of reducing agent to take that carbonyl group off. Okay, there's acylation. Now we'll do nitration and sulfonation. Again, not the most important, I don't think, but I'm still gonna go over it. Maybe a question on this. Okay, what I should know what I need for nitration. I need nitric acid. NO3. This alone will get me some nitrobenzene, but not a lot. Okay, that proton transfer between two molecules to start out between the same molecule, that's going to be really slow. So what do I do to increase the chance of a proton transfer? Add a strong acid like H2SO4. Okay, that way that proton transfer first step, is going to happen between this and nitric acid. And then we'll do heterolysis from there. We'll create water. Water will be our base. let's do this mechanism really quickly. So 4 is going to donate. I should know the structure for nitric acid as well. Okay, that's going to be good to know. NHO3, H group, O minus, there, plus. Okay, so it's a little funky. Yes, it's a neutral charge overall, but know that nitrogen has a positive charge and we do have an O minus. My second step is heterolysis. In this case, hydrolysis. So water is going to leave. That should help me identify on which oxygen is actually taking a proton in. I'm going to use my OH group to perform this proton transfer. I'll have water as a good leaving group. There's water here. It's a good leaving group. Now I perform a heterolysis. I can kick water off. What do I do to use that? To do that, lone pair on this oxygen here, form a double bond, and kick water off. There's my heterolysis step. Now I have NO2. Let me actually draw that out. And I have water. Next step is addition. Okay. Make sure to bump up that bond on the oxygen. This is going to be a slow step because I disrupted aromaticity. I added my nitro group on there, so NO2. Okay. And notice this NO2, it's still N plus and O minus. And then what am I going to use as a base to restore aromaticity? The water I made in the previous step. So I have that hydrogen there, hydrogen, restore aromaticity, and I have nitrobenzene. Boom. Okay, sulfonation. Sulfonation with just sulfuric acid, same thing, okay? Again, detailed mechanism, look at your book. The addition of sulfuric acid here is what makes it a lot faster. That proton transfer happens readily, rather than two molecules having to do it themselves. So we use sulfuric acid to make nitration faster. What do we use to make sulfonation faster? We use fuming sulfuric acid, okay? And remember, we don't have to really do a heterolysis step, and if we use that as well. So H2SO4 for sulfonation, and then I use SO3, that's that fuming sulfuric acid that's going to speed up this reaction. So SO3, sulfur can make 6 bonds, oxygen likes to make 2. There's fuming sulfuric acid. I do a proton transfer between this and my proton source here. So I have my oxygen, it's going to protonate, and I'll be left with positive charge there, okay? Sweet, cool. I don't need to, I've done the proton transfer, I can go straight to addition now. Remember, I don't have to do that heterolysis step. Benzene is going to attack still the central atom, sulfur. And which bond is going to be best to push? We move this one, notice we'll eliminate that positive charge. So now I'm here, added my sulfur group. Okay. Sweet, and then what am I going to use as my base? I'm not given anything else, so the conjugate base of sulfuric acid would be okay. It doesn't really show it in your book. I imagine fuming sulfuric acid could as well take that hydrogen. The fact that this mechanism is probably more than likely to be on there and you have multiple options, I don't think it really matters much. Okay, we'll finish with elimination and you end with sulfonation. Okay, mechanism to know, not that important for synthesis because what can we do with sulfate group on there? Nothing right now. Okay, last two things we're going to cover, benzoic acid production, two ways of doing it, and then this benzene diazonium ion. I'm going to actually make that a different video. This is taking a lot longer than I expected, so I'm going to stop this one. I'll make another video on those last two topics.